There is a particular quality to Scottish Highland mornings that resists description. The light comes in sideways, pale and searching, cutting through the heather at an angle that makes everything appear both ancient and newly discovered. The hills hold their silence the way old houses hold their stories, quietly, stubbornly, only releasing them when you stop expecting to hear anything at all. Picture a hiker on one such morning, somewhere in the rough country near Inverness. Boots dark with dew, breath clouding in the cool air, moving slowly across the summit ridge of a hill that looks, at first glance, like every other hill in this part of the world. Loose stone underfoot, patches of tough grass bending in the wind, the occasional scatter of ancient rubble, where walls once stood and have since surrendered to gravity. And then a stop, not a dramatic one, not a gasp, just a halt, the way you pause when something small catches the edge of your attention and you aren't yet sure what it was. They crouch down. Run a finger along a piece of stone at the wall's base. And something is wrong in the most compelling sense of that word. The stone is smooth in a way stone should not be. Not worn smooth by water, not polished by centuries of wind, fused, as if it had, at some point in its distant past, forgotten how to be stone and briefly become something else. Something liquid. Something that flowed and then stopped, and then remembered too late what it was supposed to be. Hold that image for a moment, because it is not a fantasy, and it is not an exaggeration. These stones exist. Thousands of them, in walls and ramparts scattered across the hilltops of Scotland and beyond. They glow faintly in direct sunlight, the way glass does. They feel different under the hand, cooler, sleeker, almost artificial. When you look closely at a cross-section, you can see how different minerals, quartz, feldspar, dark flecks of mica, have lost their individual borders and merged into a single, continuous mass, like colours blended past the point of separation. There are no cracks between them. There are no seams. Whatever happened to them happened at temperatures so extreme that the idea of individual stones simply ceased to apply. Geologists who first encountered these structures in the field have described the experience in terms that are almost reluctant, as if they felt they ought to have a ready explanation and were quietly embarrassed that they did. Not. The material doesn't match volcanic glass. It doesn't match lightning-struck sand. It doesn't match any natural geological process that leaves behind such large, structured, wall-shaped formations on hilltops that are clearly, unmistakably, the ruins of things people built. It is, in the most precise and inconvenient sense of the word, anomalous. These glittering walls sit on hilltops across Scotland, across Ireland, across France and Sweden, and places even further afield. There are hundreds of them. Some are large enough that their outer circuits stretch for hundreds of meters across the high ground. Some are small, personal almost, as if a single family's home was sealed with the same impossible process. They are called Vitrified Forts. They have been puzzling serious researchers for 2.5 centuries. And the truth of how they were made, if truth is the right word, for something still argued over in university papers, and archaeological field reports may be stranger and more extraordinary than anything a person kneeling on that hillside, running their finger along the smooth fused stone, could easily imagine. This is not the story of what we know. It is the story of what we are only now beginning, carefully, to understand. And it begins here, on a hill that glitters in the morning light, with a question that has no comfortable answer. How does stone melt? And who was here when it did? The year was 1777. Scotland was a country in the process of becoming something new. Enlightenment ideas moving through Edinburgh drawing rooms, scientific societies forming, men of learning beginning to turn their instruments toward everything the world contained. It was, in many respects, exactly the right moment to notice something strange and decide it deserved a systematic explanation. John Williams was a mineralogist. Not a famous one, not the kind whose name appears in schoolbooks, but a careful and methodical man who spent considerable portions of his life walking the hills of Scotland with a geologist's eye and a naturalist's curiosity. What he encountered on those hills in the latter half of the 18th century unsettled him in ways that his training had not prepared him for. He found walls on hilltops, ancient walls, clearly constructed by human hands, whose stones had been fused together as if by heat of extraordinary intensity. He collected samples. He examined them. He wrote pages of notes that returned, again and again, to the same inadequate conclusion. He did not know what had done this. He published his findings. He proposed theories. He revised them. He proposed different theories. The stone clearly showed the effects of extreme heat, there was no question about that. But the explanations he reached for all broke down under scrutiny, one after another, like supports that looked solid until weight was placed on them. He died having never resolved the question to his own satisfaction. Over the following century, other researchers followed in Williams's footsteps, drawn by the same combination of visible evidence and stubborn inexplicability. Geologists came and made their arguments. Archaeologists came and made different ones. Military historians arrived with theories about sieges and conquest and the burning of enemy fortifications. Each brought a different set of tools. Each left with the uncomfortable sensation of having explained something that was not, in fact, explained. The structures they were studying had a name by now: Vitrified Forts. The word vitrification comes from the Latin for glass vitrum and describes the process by which certain silicate-rich materials, when subjected to sustained temperatures of extreme intensity, undergo a transformation that is as simple to describe as it is extraordinary to contemplate. The molecular structure of the stone breaks down. The rigid crystalline arrangement of minerals, the orderly stacking of atoms that gives rock its solidity, collapses under heat. The mass softens. It begins, slowly and thickly, to flow. And when it cools, it resolidifies not as the original rock, not as the collection of separate minerals it once was, but as something new, something unified, a material that is partly stone and partly glass, and wholly unlike what came before. This is not a subtle change. Under a microscope, the difference between vitrified and unvitrified stone is unmistakable. It is the difference between a mosaic and a painting, between individual pieces arranged together and colours that have genuinely merged. And achieving this transformation requires temperatures that, as researchers through the 19th and early 20th centuries calculated with increasing precision, should have been beyond the reach of any technology available in the ancient world. The numbers kept coming back wrong. The evidence kept pointing somewhere that the standard explanations could not follow. By the mid-20th century, the vitrified forts occupied an awkward place in the archaeological literature, acknowledged, documented, and quietly set to one side. The number of serious, peer-reviewed publications on the topic was strikingly small given the scale and distribution of the phenomenon. It was not that researchers had forgotten the forts. It was something more uncomfortable than that. It was that the forts, under scrutiny, had a habit of making researchers look incompetent. The mystery did not yield. And in academic life, unsolved mysteries have a way of becoming invisible, not because they are unimportant, but because admitting you cannot explain something is professionally costly in ways that simply not mentioning it is not. That silence is itself a kind of evidence. When a category of physical structures, hundreds of them, documented across multiple countries and cultures, fails to generate a satisfying scholarly consensus across 250 years of serious investigation, something meaningful is being said, not necessarily about ancient technology, but certainly about the limits of the frameworks we have used to understand it, and perhaps about the courage it takes, in any field, to follow the evidence past the point where comfortable explanations run out and the genuinely strange begins. John Williams had that courage. In his way, he published what he found, even when he could not explain it. The researchers who came after him, by and large, did not follow his example. They found the strangeness professionally inconvenient, and they moved on. The walls, indifferent and patient, continued waiting for someone willing to sit with the discomfort long enough to see what it was pointing toward. There are several theories about how vitrified forts were created. Some are old, some are recent, some are well supported, some are not. And one of them, the one this documentary will spend the most time with, is, by any fair assessment, the most technically daring, the most physically coherent, and the most uncomfortable of them all. The theory is this: that the people who built these forts, working in the Iron Age and possibly earlier, used knowledge of focused solar energy to deliberately melt the outer faces of their stone ramparts. That they built or employed mirror systems arrays of polished reflective surfaces, arranged and directed with precision to concentrate sunlight to temperatures capable of liquefying stone. That the vitrification was not an accident of warfare, not a byproduct of ritual fires, not a quirk of geology, but a deliberate engineering process carried out by people who understood, in practical, and perhaps in spiritual terms, how to make the sun do work. This is not a fringe idea invented by internet speculation. It has serious roots in published research, in experimental archaeology, in materials science, and in the growing body of evidence about what Iron Age and Bronze Age peoples were actually capable of, as opposed to what we have historically assumed they were capable of, which are two very different things. The evidence for it is not complete. No honest account of this subject could claim otherwise. But the evidence against it, the evidence that would allow us to say with confidence that this could not have been done, does not exist either. And that gap, that space between what we can demonstrate and what we cannot rule out, is exactly where the most interesting history lives. What follows is not a simple lecture. It does not start with a conclusion and work backward. It starts, instead, with the physical reality of the vitrified stone itself. What it is, what it tells us, what it refuses to tell us, and moves outward from there, through the geography of its distribution across the ancient world, through the physics of solar concentration, through the archaeology of ancient optical knowledge, through the experimental attempts to replicate the process, and finally into the deepest question of all. Not just how the walls were made, but why. What it meant to the people who made them, what they were building, and what they were asking the sky to do. Some researchers who have spent years with this material have described the experience of studying vitrified forts in terms that stay with you. One said, more than once, that looking closely at the best examples felt like looking at something that shouldn't exist yet. Not supernatural, not impossible, just ahead of where it ought to be. That phrase lands with weight when you hold a piece of ancient fused stone in your hand and feel how smooth it is, how complete, how final. Something was done here that we have spent centuries failing to properly explain. And the explanation, when it comes as it must, because the walls are real and physics is patient, will almost certainly require us to revise the story we tell about ancient human capability, quietly, permanently, and without apology. There is an old geology department at a Scottish university, the kind of room that feels as if it has been thinking long, slow thoughts for decades. Wooden cabinets with shallow drawers hold labelled specimens in rows. The smell is mineral and faintly dusty, layered with the residue of 100 years of curious hands. The instruments are newer than the furniture, but only barely. And somewhere in that room, in the early 1980s, a researcher placed a fragment of ancient wall under a scanning electron microscope and saw something that stopped him mid-breath. The sample came from a hilltop fort. It was unremarkable to the naked eye, a piece of greyish stone, perhaps the size of a palm, slightly heavier than it looked. But under magnification, the surface told a story that the outward appearance concealed entirely. The boundary between two adjacent stones, which should have appeared as a visible seam, a line of separation between one mineral composition and another, did not exist. The quartz and the feldspar and the dark flecks of iron-bearing mineral had merged, not cracked together, not compressed together, merged, the way colours merge when you mix paints past the point of recovery. The material between and around them was glassy smooth at the molecular level, in a way that only occurs when crystalline structure has been completely abandoned and then readopted under cooling conditions. To understand what this means, consider how glass is made. Sand is silica. Heat sand to sufficient temperature, and its crystal structure breaks down the silicon and oxygen atoms that were locked in rigid geometric patterns lose that rigidity and begin to move. The material flows. It becomes a liquid, thick and slow and reluctant, not like water but like honey that has forgotten it was ever sand. Let it cool slowly, and it resolidifies not as crystalline quartz but as amorphous glass. No internal structure, no grain boundaries, no distinction between one region and another. A single, continuous, unified material that was many things before and is now only one. That same process, applied to stone wall material at sufficient temperature, produces vitrification. The distinction from natural processes is critical. Volcanic glass obsidian forms when lava cools rapidly. It has a specific chemical signature reflecting the specific mineral composition of the magma that produced it. Fulgurite glass formed by lightning strikes is hollow and branched, following the path of the electrical discharge, with its own distinct morphology. Neither of these resembles what appears in vitrified hill forts. The glass in these walls is located precisely where human-built stone walls existed. It incorporates the exact mineral compositions of the local building stone. It appears in configurations that are architectural following wall lines, penetrating into the gaps between courses, fusing structural components together in patterns that reflect the geometry of deliberate construction, and it required, to form, sustained temperatures somewhere between 1000 and 1200 degrees Celsius. Not briefly, not in a flash. Sustained, held at that temperature long enough for the stone to genuinely flow, and the fusion to penetrate deeply into the wall's fabric. For comparison, a wood fire in open air burns at around 600 to 700 degrees. A well-managed charcoal forge, with bellows providing forced airflow, can reach 900 to 1000 degrees. Getting significantly beyond that with pre-industrial technology is not trivial. It requires either very specific fuel combinations burned under carefully controlled conditions, or something else entirely, something that concentrates heat rather than simply producing it. The question that has sat at the center of vitrified fort research for 2.5 centuries is not whether these temperatures were reached. The evidence for that is written in the stone itself. The question is, what reached them? And whatever the answer, it was not accidental, not random, and not simple. There is a final observation from the laboratory that belongs here before moving on. When researchers examined samples from multiple different vitrified fort sites and mapped the chemical composition of the fused zones, they found a consistency that surprised even those who expected the results to cluster. The glassy material was not unique to each site, in ways that would suggest entirely different heat sources and mechanisms operating independently. It shared characteristics, thermal signatures, flow patterns, degrees of mineral mixing that suggest, across sites separated by hundreds of kilometers, a broadly similar process was operating. Not identical. Not evidence of a single operator or a single event, but similar enough in its physical character to suggest that the knowledge behind it, whatever that knowledge was, had a shared origin, or was transmitted through networks of contact and exchange that connected these hilltop communities across the wider landscape of Iron Age Celtic Europe. The stone, in other words, remembers not just what happened to it. It remembers, in outline, where the knowledge came from. It is only fair to begin with the most obvious explanation. Hilltop forts were built largely of timber. Iron Age construction typically wove wooden beams through the interior of stone ramparts, a technique called timber lacing, to provide flexibility and resistance to the kind of lateral forces that would otherwise cause dry stone walls to collapse outward. These beams were integral, load-bearing, threaded through the stone fabric in regular patterns, and wood burns. Everyone who has ever watched a bonfire knows that wood, under the right conditions, burns with considerable intensity. In a structure where timber is woven through stone on a hilltop, where wind provides natural bellows effect, the potential for a very hot, very prolonged fire is not difficult to imagine. This is the core of the warfare theory, the explanation that dominated academic discussion for much of the 20th century. Enemies attack a hill fort, set fire to the timber-laced walls, the fire burns long and hot enough to vitrify the stone, and what we see today is the archaeological trace of violence, not engineering. It is a compelling argument in its broad outline. It requires no exotic technology. It fits with the general evidence for Iron Age conflict. Several vitrified fort sites do show additional evidence of violent destruction weapons, burned organic material, signs of rapid abandonment that are at least consistent with a hostile burning event. But then the details arrive, one by one, and the argument develops fractures. The first problem is depth. In many vitrified forts, the fusion is not confined to the surface stones nearest to where timber would have burned. It extends deep into the wall fabric, affecting stones that would have been well insulated from any fire burning in the timber channels. Heat travels through stone slowly and poorly. A fire burning in a timber framework embedded in rock does not simply heat the adjacent stone to vitrification. Temperatures the stone itself acts as an insulator, drawing heat away from the burning material. To penetrate the wall's depth with sufficient heat to achieve fusion, the temperature at the source would need to be far higher and sustained for far longer than any wood fire would reliably produce. The second problem is uniformity. When catastrophic fires occur in structures, the burning is chaotic. Wind shifts, fuel density varies. Some sections burn hot, others barely catch. But the vitrification in many hill forts is remarkably consistent across extended sections of wall, not perfectly uniform, but far more regular than a chaotic blaze would produce. The distribution of fused stone suggests something directed, something that was applied with at least a degree of deliberate control. The third problem is fuel. Consider the scale of what would be required to maintain vitrification temperatures across even a modest length of stone rampart. The calculations are sobering. To heat a cubic meter of granitic stone to 1000 degrees through direct conduction from burning timber would require a quantity of dry hardwood that most estimates place in the range of several hundred kilograms per meter wall. A full circuit of wall, hundreds of meters long, would require fuel quantities that strain the logistics of any conceivable siege scenario and would leave behind enormous deposits of charcoal and ash. These deposits, in the quantities that the fire theory predicts, are largely absent from the archaeological record. And then there is the experimental evidence, which is perhaps the most damaging challenge of all. In the 1990s, researchers in Scotland constructed faithful replicas of Iron Age timber-laced stone walls and burned them under controlled conditions, monitoring temperatures throughout the process. They succeeded in producing partial vitrification in some cases, but the fusion they achieved was always most intense at the interior face of the wall where the burning timber was located. The original structures show the opposite pattern. The heaviest vitrification, consistently, is on the outer face. The heat in the ancient forts came from outside, not from within. The implications of that single finding are difficult to overstate, and they point away from fire and towards something else entirely. Modern science has given archaeologists something that would have seemed close to miraculous to the researchers of 2 centuries ago: the ability to read the thermal history of a piece of stone the way a doctor reads an X-ray. The field is called archaeometry, and while the name is technical, the concept is elegant: the application of physics and chemistry to ancient materials, asking those materials to reveal the conditions under which they were formed, altered, or destroyed. Several techniques have been applied to vitrified wall samples from sites across Britain and continental Europe, each asking a slightly different question of the same ancient material. Scanning electron microscopy allows researchers to examine the fused stone at near-atomic resolution, mapping where different mineral compositions begin and end, or, in the case of vitrified material, where they fail to begin and end at all. X-ray diffraction identifies whether the material retains any crystalline structure or has become fully amorphous glass. Thermoluminescence dating, which measures the accumulated radiation trapped in a material since it was last heated, provides information not only about when the vitrification occurred, but about the rate at which the material subsequently cooled. That cooling rate matters more than it might initially appear. When a material is heated to extreme temperatures and then cooled quickly, as happens in a sudden, uncontrolled fire that burns out and leaves the stone to cool in open air, it develops a particular internal microstructure. When the same material is cooled slowly and steadily, as happens when heat is withdrawn gradually, and the stone is allowed to cool in a managed, sustained way, it develops a different one. The difference is measurable. It is written into the glass itself, in the orientation of flow features and the size of any remaining mineral crystals. Multiple vitrified fort samples have been examined for exactly this signature. The results carry a quiet weight that is difficult to dismiss. Many samples show microstructures consistent with controlled, gradual cooling, not the rapid quench of a fire that burned itself out, but the measured retreat of heat from a source that was actively managed. One sample from a site in Aberdeenshire showed what the researchers described as a laminar flow pattern within the fused material, a directional structure suggesting that the molten stone had moved slowly in a consistent direction before cooling, like a very slow, very thick liquid flowing downward under gravity over a period of hours. Even more telling is a specific finding from chemical profiling of wall cross-sections at several sites. When researchers mapped the temperature gradient across a wall's thickness estimating the peak temperatures reached at different depths from the surface. They found a pattern that does not fit an interior fire. The highest estimated temperatures were at the outer wall face. The temperatures declined, moving inward. This is the thermal signature of heat arriving from outside and penetrating inward through conduction, not heat generated within and radiating outward. It is a subtle distinction, but it is physically unambiguous. Whatever reached these stones with sufficient intensity to melt them, it arrived from the direction of the sky and the open hillside, not from within the wall, not from a fire set by attackers or defenders on the inside, from somewhere above and beyond. The seed of an answer has been planted in the chemistry of the stone itself, and it is pointing upward. If you were to draw a map of the world and mark every confirmed site where vitrified stone structures have been identified, the result would surprise you. But it is in Scotland that the marks cluster most thickly, and it is there that the phenomenon has been studied most deeply, and it is there that the landscape itself seems to carry the memory of whatever happened with the greatest physical presence. More than 70 confirmed vitrified hill fort sites have been documented in Scotland alone, with additional candidates awaiting detailed analysis. They spread across the country from the Northern Highlands to the borders, but they concentrate particularly in the northeast Aberdeenshire, Angus, Perthshire, where the geology provides an abundance of silicate-rich granite and gneiss, exactly the materials that vitrify most dramatically under extreme heat. Some sites are large enough that their outer walls enclose hilltops, commanding wide views across river valleys and coastal approaches. Others are smaller, almost intimate, perched on defensible ground with sightlines rather than size as their primary advantage. Tapo Noth in Aberdeenshire rises to over 500 metres above sea level and commands a view that in clear weather extends to the North Sea coast. Its summit is ringed by a rampart wall whose vitrification is so extensive, so deep, and so dramatically visible that Victorian-era geologists, who first visited the site in the 1800s, debated seriously whether they were looking at the remnants of a lava flow. The hill does not sit on any volcanic feature. The rock is local granite. What happened to it happened above ground, within a structure that was built, inhabited, and then subjected to something that stone walls are not supposed to survive. The moment when someone noticed that the stones beneath the glass were carefully squared and deliberately placed, that this was not geology. But archaeology is one of the great quiet shocks in the history of Scottish fieldwork. Craig Fadrig, on the western edge of Inverness, offers a different character, smaller, more intimate, its vitrified wall fabric, less spectacular in scale, but no less technically puzzling. Finarvan in Angus has been excavated and dated, offering some of the most reliable temporal anchors in the debate about when these structures were modified. Dunmac Snyachan in Argyll sits in a landscape of lochs and ancient forest, its fused walls looking out over water that has not changed its course since the Iron Age. Each of these sites, visited in sequence, creates a cumulative effect that data tables and journal papers cannot fully replicate. There are simply too many of them. They are too consistent. They are too deliberately built and too dramatically altered to be explained away as coincidence or confusion. The construction technique they share, timber-laced, dry stone walls, the wooden beams woven through the stone fabric in horizontal rows, was widespread across Iron Age Celtic Europe. It provided flexibility, resilience, and structural coherence that purely dry stone construction could not match. It is also, critically, a technique that interacts with extreme heat in specific ways. The timber burns and leaves voids within the wall. The stone is left with channels of reduced density running through it, pathways along which heat can travel differently than it travels through solid rock. Understanding that architecture is essential to understanding what happened to it. But the architecture alone does not explain the temperatures. And the temperatures, as the chemistry insists, came from somewhere outside. What also strikes the careful visitor to these sites is the deliberateness of their selection. These are not random hilltops. Each one commands a specific field of view, a river valley, a coastal approach, a mountain pass that would have made it significant to communities whose survival depended on controlling movement through their territory. The effort of construction was concentrated at places that mattered for reasons independent of geology. People chose these hills for what could be seen from them, and perhaps In choosing elevated hilltops exposed to the maximum arc of the summer sky, they also chose locations where a very specific kind of work could be conducted most effectively. The sun on a highland hilltop in July is not the same sun that struggles through the trees in a valley below. It arrives early. It stays late. It burns with a clarity and an intensity that anyone who has spent a day at altitude on a clear summer day in Scotland will recognize immediately. These hills were not just watchtowers. They were stages elevated, exposed, commanding where sky and stone could meet without obstruction, and where, if the builders understood what they were doing, the most powerful tool in the ancient world was available every clear day from dawn until dusk. Scotland is where the story is densest, but it is not where it ends. Move south and east across the water to continental Europe, and the same pattern emerges: hilltop forts with vitrified walls, scattered across landscapes that had no known contact with the Celtic peoples of Atlantic Scotland during the periods in question, yet showing the same physical transformation of the same building material by what the chemistry consistently identifies as the same type of directional, intense, sustained heat. In France, the relevant structures are known as oppida large, strategically positioned Iron Age settlements that served simultaneously as trading centres, administrative hubs, and fortified refuges. Several oppida in Brittany and in the volcanic plateau country of the massive central show vitrified rampart sections, whose extent and character have puzzled French archaeologists since the first systematic surveys of the early 20th century. The site at Peyran in Côte d'Armor in Brittany attracted particular attention when excavations revealed rampart vitrification so extensive and so technically accomplished that one research team proposed, somewhat reluctantly, that the site might represent evidence of an ancient industrial process rather than a one-time event. The vitrification at Peyran is not incidental. It is structural. It extends across sections of wall that would have taken enormous and sustained effort to treat in this way. Moving north, Sweden offers the fort known as Broborg in Uppland, which became the site of one of the most carefully documented experimental archaeology projects ever conducted in relation to vitrified structures. Swedish researchers, working with reconstructed wall sections built to authenticate Iron Age specifications, conducted a series of controlled firing experiments across multiple years, attempting to determine what could and could not be achieved through conventional combustion. Their results, published in peer-reviewed journals, have become foundational to the debate. They could achieve vitrification, but not easily, not completely, and not in ways that fully matched the original. Something in the original process was different, and the difference was not one the conventional fire explanation could account for. Germany contributes examples from the hill forts of the Rhineland and the Mosel Valley. Portugal shows sites along its northern highland ridges. The Czech Republic has documented vitrified wall sections in Iron Age hill forts that have received frustratingly little attention in the wider English language literature. Each of these sites, taken alone, might be explicable within conventional frameworks. Taken together, they describe something far more significant: a technique, or a knowledge, or a capacity that existed across Celtic Europe during the Iron Age, with sufficient consistency to leave the same physical trace in the walls of communities separated by hundreds of miles. And then there is the detail that the narrator plants here because it does not yet have its full context, but deserves to be noted before its moment arrives. The vitrified forts of Europe, the ones with the most dramatic and extensive vitrification cluster in areas that receive, for their northern latitudes, an unusually high number of clear sky days during summer months, Atlantic coastal regions, elevated highland terrain where morning cloud often burns off by midday, places where the sun, on its strongest days, is genuinely powerful. This correlation is not proof of anything. It is a pattern. Patterns, in archaeology, are the beginning of questions. And this particular pattern points quietly, persistently toward the sky. Here is the thing that stops many researchers mid-sentence when they first encounter it. Vitrified stone structures are not a European phenomenon. They appear in Africa. They appear in the Middle East. There are credible reports, some well documented, some requiring further investigation from South America. Whatever process melted these walls in the Scottish Highlands, some version of it appears to have operated elsewhere, in cultures that the current state of archaeological evidence cannot plausibly connect to Iron Age Scotland. This is not a conspiracy theory. It is an observation about the distribution of a physical phenomenon, and it deserves to be handled with the same intellectual care as any other piece of evidence neither inflated nor dismissed. In southern Africa, the ancient stone structures of the Zimbabwe Plateau have attracted enormous archaeological attention over the past century, much of it overshadowed by the deeply uncomfortable politics of colonial-era scholarship. When European explorers and administrators first catalogued these structures in the late 19th century, a combination of prejudice and institutional incentive led many of them to attribute the most sophisticated features of the Zimbabwe culture to outside influences: Phoenicians, Arabs, ancient Egyptians, rather than to the African peoples whose ancestors demonstrably built them. That history of intellectual dishonesty has permanently complicated the scholarship. But underneath the politics, the archaeology is real. And in some sections of some structures associated with this building tradition, researchers have identified partial vitrification stone fused at temperatures above those achievable by conventional wood fires, with no clear explanation within the natural geological history of the region. When this vitrification was noted in the colonial-era literature, it was almost universally attributed to natural causes, to the volcanic glass content of local building stone, or to geological processes unrelated to construction. When similar features were noted in Scottish hill forts, the same researchers would confidently describe them as evidence of extreme human-generated heat. The double standard is remarkable. It is also, when stripped of its historical context and examined purely as an intellectual error, instructive. It demonstrates how powerfully our assumptions about what a given people could or could not have accomplished shape what we see when we look at the evidence they left behind. The South American examples are more complicated, and the narrator acknowledges that complication honestly. Some reported vitrification in Andean stonework reflects the natural properties of volcanic building materials, rather than heat-induced transformation. Andean builders used obsidian and naturally glassy volcanic rock extensively, and distinguishing between natural glass in the building material and heat-induced fusion requires chemical analysis that has not been carried out consistently across the relevant sites. There are, however, specific locations, particular wall sections in pre-Incan structures, where the vitrification pattern is inconsistent with the natural material and where the thermal signatures are, to put it carefully, unexplained by current frameworks. What does the global distribution mean? At minimum, it means that the vitrification of stone structures in the ancient world was not a uniquely Scottish curiosity or a local Celtic practice. It was a human phenomenon, one that manifested in various forms and to various degrees of intensity across cultures and continents that shared nothing obvious except the availability of sunlight, the knowledge of fire, and the desire to make walls that would last. That is not nothing. That is, in fact, exactly the kind of distribution pattern you would expect from a technology that emerged from the most universally available energy source on the planet. Something, in the ancient world, understood what sunlight could do, and it left its signature in stone on every inhabited continent on Earth. Great discoveries in science very often arrive through questions that seem, at the moment of asking, to be slightly beside the point. The history of physics is full of researchers who started by measuring something peripheral and ended up overturning something central. The Vitrified Fort debate has its own version of this story, quieter, less celebrated, but no less instructive about how the most important insights tend to slip in through the side door. In the 1990s, a Swiss researcher named Eveline Kramer was working through a body of data on vitrified hill fort sites, not the dramatic large-scale sites like Tapo North, but a wider sample, including many lesser-known examples across Scotland and northern France. Her initial interest was not in the mechanism of vitrification, but in the spatial distribution of vitrification intensity within individual walls. She wanted to understand why some sections of a given wall were more heavily fused than others, a question that most previous researchers had treated as either random variation or a function of fuel distribution in timber-laced construction. What Kramer noticed, as she mapped the data site by site, was not random. The most heavily vitrified sections of walls tended, with a consistency that became difficult to ignore, to face a specific direction. not always exactly the same direction in absolute compass terms. The hills themselves varied in orientation, but consistently facing toward the direction of peak solar exposure during the long days of summer. The walls that caught the most direct summer sunlight were the walls that had been fused most completely. She checked this against the solar azimuth data, the calculated direction from which sunlight strikes a surface at maximum intensity during the summer months at Scottish and northern French latitudes. The correlation held. She expanded the sample. The correlation held more firmly. She wrote it up and submitted it, cautiously framed, acknowledging that correlation was not causation, and that the finding required explanation rather than constituting one. The reception was muted, politely muted, which in academic terms is its own form of cold water. The finding was noted, cited occasionally, and then did what uncomfortable findings often do in disciplines that are attached to their existing frameworks. It settled into the literature without generating the follow-up investigation it deserved. The resistance was not irrational. If Kramer's orientation correlation reflected something real about the mechanism of vitrification, the implications were significant. It meant that the heat responsible for melting these walls had been preferentially applied to wall faces oriented toward the sun. It meant the heat had a direction. And a direction meant, almost certainly, a source that was not simply a burning building. But that is what the data showed. Not what someone imagined, not what a theory predicted, what the measurements themselves produced when the question was asked sideways, not what burned. But where did the heat arrive from? Was a pattern pointing toward the most powerful and most ancient heat source available to anyone standing on a hillside in the northern hemisphere on a clear summer day. The solar theory did not begin with a bold claim. It began with a patient woman checking which way the walls faced and finding that they faced the sun. Think back to childhood. Think of a magnifying glass held over a piece of paper on a sunny day, the trembling bright spot on the paper's surface, the faint curl of smoke, the small dark scorch mark appearing almost instantaneously. That memory is not merely nostalgic. It is the seed of one of the most powerful heat generation principles ever discovered, and it has been within human reach since the moment our ancestors first noticed that curved, polished surfaces do something unexpected to light. The principle is refraction and reflection. When light rays travel through glass or bounce off a curved mirror, they change direction. A flat mirror reflects light at equal angles. It redirects it but does not concentrate it. A curved mirror, shaped in the specific mathematical curve known as a parabola, does something far more interesting. It takes parallel incoming rays of light and redirects every single one of them toward the same point, the focal point. And at that point, all the solar energy that fell across the entire reflective surface arrives simultaneously, concentrated into a space that might be only millimeters across. The energy per unit area at the focal point is the total energy falling on the mirror divided by the area of the focal spot. A large mirror produces a very small, very hot spot. This is not theory. It is measurable, reproducible, demonstrable physics. The solar furnace at Odilo, in the Pyrenees of southern France, is one of the most powerful solar concentrators in the world. It consists of an array of flat mirrors, a heliostat field arranged on a hillside to track the sun and direct its light toward a single, large parabolic mirror, which focuses it onto a small target area. The temperatures achieved at that target exceed 3,500 degrees Celsius. Steel melts at 1,500. Stone vitrifies at around 1,000. The Odilo furnace, using sunlight alone and no fuel of any kind, operates comfortably at more than twice the temperature needed to melt rock. The sun, properly organized, is a kiln of nearly unlimited power. The question for the vitrified forts is not whether this principle could achieve the required temperatures. It absolutely could. The question is whether it could have been applied in the ancient world using materials and construction methods available to Iron Age or Bronze Age people. And this is where the analysis becomes interesting in a different way. A parabolic mirror does not require advanced metallurgy. It requires a reflective surface of sufficient area shaped into an approximately parabolic curve. Ancient metalworkers could hammer copper and bronze into curved sheets. They could grind and polish obsidian volcanic glass to optical flatness. They could construct wooden frames shaped by eye and by measurement into curved forms, and then cover those frames with tightly stretched, mica-dusted leather. Any of these approaches would produce a reflective surface capable of concentrating sunlight, not with the precision of a modern solar furnace, but with enough concentration at sufficient scale to raise temperatures well above the vitrification threshold of granitic stone. The key variable is scale. A mirror 1 meter in diameter, polished to reasonable reflectivity, can concentrate enough sunlight to melt lead on a clear summer day. A mirror 3 meters in diameter, concentrating the same sunlight, produces roughly 9 times the heating power at its focal point. An array of 10 such mirrors, coordinated to direct their focal spots at the same section of wall face, produces 90 times the power of the single small mirror. The mathematics here are not speculative. They follow directly from the laws of optics and thermodynamics, and they point toward a conclusion that is, depending on your prior assumptions about ancient people, either surprising or inevitable. With enough polished bronze and enough understanding of where to point it, the sun was always capable of doing this. The idea that ancient people might have understood how to concentrate sunlight sometimes meets a reflex of disbelief, a sense that this knowledge belongs to the modern era, that it required the scientific revolution to discover that no one in the Bronze Age or Iron Age could have stumbled onto something so sophisticated. This reflex is understandable. It is also demonstrably wrong. In 1853, the British archaeologist Austin Henry Layard was excavating the ruins of Nineveh, the ancient Assyrian capital near modern Mosul in northern Iraq, when his team uncovered a small, peculiar object. It was made of polished rock crystal, ground into a plano-convex lens shape approximately 3 centimeters in diameter. It was beautifully made. Layard catalogued it and moved on, assuming it was decorative. More than a century later, physicist Giovanni Pettinato examined its optical properties and found that the grinding was sophisticated enough to produce genuine magnification. The lens focuses light. It concentrates it. Whether it was used for starting fires, for magnification, or for both is debated. What is not debated is that someone in Nineveh, around 700 BCE, manufactured a functional optical device, deliberately, with knowledge of what ground crystal does to light. The Nimrud lens, as it came to be known, is not alone. Similar polished crystal objects have been found in Bronze Age contexts across the Mediterranean and the Near East, in quantities and with optical qualities that cannot all be dismissed as accidental. Then there are the texts. The Athenian playwright Aristophanes wrote a comedy called The Clouds in 423 BCE. Comedy, by its nature, makes reference to things the audience already understands. Jokes about objects no one recognizes are not funny. In one scene, a burning glass is used to melt wax. The audience laughed. They laughed because they knew what a burning glass was. This is not a marginal document. It is one of the best preserved works of classical comedy, and it treats the concentration of sunlight through a glass lens as a piece of everyday knowledge familiar enough to be funny. And then there is Archimedes. The story of the burning mirrors of Syracuse, the legendary weapons with which Archimedes allegedly set fire to the Roman fleet during the siege of the city in 212 BCE, has been dismissed and revived and dismissed again, across 2 millennia of historical debate. In the early 2000s, a team at MIT set out to test whether polished bronze mirrors arranged as a heliostat array could actually ignite a wooden ship at a distance of around 30 meters. After multiple attempts, they succeeded. The wood caught fire. The principle worked. It worked because the principle is sound, not because the legend is reliable as history, but because the physics it describes is real, and because Archimedes, if the story has any foundation, was working with a technology that already existed and was already understood. The burning mirror was not his invention. He may have scaled it, but the knowledge behind it belonged to his world, not to the one that came after. The pattern across these examples is consistent and significant. A polished crystal lens in Assyria, a burning glass in an Athenian comedy, a legendary mirror weapon in Sicily. These are not 3 isolated curiosities scattered across the ancient world by accident. They are 3 points on a line of optical knowledge that was not theoretical, not confined to a single culture, and not the property of one exceptional genius. It was distributed, practical, and familiar enough to be referenced casually in comedy, and deployed seriously in warfare. The question, applied to vitrified hill forts, is not whether the people who built them had any access to the principle of solar concentration. On the available evidence, that principle was part of the broader knowledge environment of the ancient Mediterranean and European world. The question is whether the Celtic peoples of Atlantic Europe, working with their own tradition of accomplished metallurgy and their documented expertise in solar astronomy, independently developed the principle or received some version of it through the trade and exchange networks that connected Celtic Europe to the Mediterranean world throughout the Iron Age. Either answer is plausible. Either answer places the solar heat technology within reach of the people who built the vitrified forts, and the walls themselves remain the most direct and unambiguous evidence that someone, somewhere along that chain of knowledge, put the principle to remarkable use. 3 pieces are now in place, and they belong together. The first, stone walls in ancient hill forts were vitrified by a heat source that arrived from outside the wall, from a direction consistent with solar exposure. The second, the physics of solar concentration, using curved or arrayed reflective surfaces available to ancient metalworkers, can achieve temperatures well above the vitrification threshold of stone. The third, ancient cultures possessed functional optical knowledge, demonstrated by physical artifacts, literary references, and legendary accounts, that is entirely consistent with the controlled concentration of solar energy. Taken individually, none of these observations is sufficient. Taken together, they constitute what scientists call a mechanistic hypothesis, an explanation that connects cause and effect through a chain of steps, each of which is independently supportable. The solar heat hypothesis proposes that Iron Age builders, working within a tradition of optical and metallurgical knowledge that can be independently verified, constructed or deployed reflective mirror systems to concentrate sunlight onto the outer faces of their stone ramparts, achieving and sustaining vitrification temperatures through a process that was deliberate, controlled, and repeated over multiple applications. It is important to be precise about what this hypothesis requires. It requires no lost civilization. It requires no technologies beyond what the archaeological record tells us these people possessed. It requires polished metal documented, curved fabrication documented, knowledge of reflective optics documented, astronomical precision in tracking the sun documented in multiple forms across Celtic Europe. What it requires, above all else, is the willingness to take these documented capabilities seriously and follow the logic of what they could produce. What the hypothesis lacks, and what intellectual honesty requires acknowledging, is direct physical evidence of the mirror systems themselves. No array of polished bronze parabolic reflectors has been excavated at a vitrified fort site. No written instructions for solar wall hardening have survived. The tools of the process, made of organic and metallic materials, have not endured in the way that stone endures, but the walls have endured, and the walls remember the direction from which the heat arrived. That memory is the most important piece of evidence we have, and it points, stubbornly and consistently, toward the sky. Begin with materials. An Iron Age craftsperson working in Scotland, in Brittany, in Scandinavia, had access to a surprisingly sophisticated palette of reflective materials. Bronze, an alloy of copper and tin that was the dominant structural metal of the preceding age, and remained widely worked in the Iron Age, can be hammered into sheets, shaped over curved wooden moulds, and polished to a surface smoothness that reflects visible light with high efficiency. Ancient bronze mirrors are among the most commonly recovered objects from Iron Age burial contexts across Celtic Europe. They are not curiosities, they are routine. Their manufacture was understood, their production was widespread, and the knowledge of how light behaves at a polished bronze surface was part of everyday optical experience for the metalworking cultures of the period. Obsidian naturally occurring volcanic glass found in highland regions of Scotland, Ireland, and continental Europe polishes to optical smoothness with less effort than metal and maintains its reflectivity without the tarnishing that eventually dulls bronze. Sheets of mica schist, the silvery flecked metamorphic rock abundant in the Scottish Highlands, reflect light across their flat cleavage planes with surprising efficiency. Leather or linen, stretched taut over a curved wooden frame and coated with fine ground pyrite dust or mica powder, becomes a lightweight parabolic reflector that could be carried, repositioned, and aimed with a degree of precision unavailable in fixed installations. Now consider the engineering. A single parabolic reflector, approximately 3 meters in diameter, made from hammered and polished bronze sheets riveted over a curved wooden frame, could, on a clear Scottish midsummer day, when the sun reaches its maximum altitude for the year, concentrate sufficient solar energy to raise the temperature at its focal point to somewhere between 800 and 1100 degrees Celsius. The range depends on surface reflectivity, atmospheric clarity, and the precision of the parabolic shaping. These are not trivial variables, but they are variables within the reach of experienced craftspeople, working with materials they understood well. An array of 10 such mirrors, not mounted on permanent structures, but held and directed by operators trained to track the sun's movement across the sky could, with their focal spots combined and directed at a single section of wall face, sustain temperatures above 1000 degrees for several continuous hours. The wall face, already hot from the preceding hours of solar work, would begin to soften. The mortar-free dry stone construction would allow individual stones to sag and flow into adjacent gaps. The fusion would begin, slowly and irreversibly, from the outside inward. For the people witnessing this process, its appearance would have been extraordinary. A convergence of brilliant reflected beams, each one a concentrated bar of light, intense enough to cause immediate pain if allowed to cross the eye, directed at a section of grey stone wall. Within minutes, the stone face would begin to smoke and discolour. Within hours, in the heat of a long midsummer day, visible flow would begin the stone surface, losing its angular definition, flowing into gaps, fusing with adjacent material in the slow, thick way that cooling lava flows into crevices. And the operators, standing behind their mirrors with their backs to the sun, tracking the focal points across the wall with the patient skill of long practice, would be doing something that to outside eyes would look indistinguishable from commanding the sun itself. The dual nature of this technology, simultaneously an engineering process and an act of barely describable power, is not incidental. It is central. In a world where fire was sacred, where the sun was divine, where the boundary between technical skill and spiritual authority was not merely porous but non-existent, focusing the sun's fire onto the walls of your home was not just construction. It was something much larger, something that required a different kind of explanation than engineering alone can supply. There is a further consideration that the engineering analysis tends to overlook. The precision required in operating this system was not passive. Mirrors do not track the sun on their own. The sun moves across the sky at approximately 15 degrees per hour, and a parabolic mirror directed at a specific section of wall face will lose its focal alignment within minutes, if not continuously adjusted. The operators of a solar concentrator array were not passive participants in the process. They were active, skilled, engaged practitioners who spent the working day in constant motion, tilting, rotating, minutely adjusting the orientation of their reflectors to keep the focal spots aligned with the target zone on the wall face. This is not a task that can be performed by the untrained or the unenthusiastic. It is skilled labor of a specific kind, requiring not only physical dexterity, but a developed intuitive understanding of how the sun's altitude and azimuth change through the hours of the day at this specific latitude during this specific time of year. The operators were, in the most literal sense, reading the sun and translating what they read into precise mechanical adjustments hour after hour across the long days of a northern summer. This was craft. This was knowledge embodied in practice and transmitted through years of apprenticeship. And those who held it held something that the community around them could neither replicate nor replace. Let the objection be stated plainly, because it deserves plainness. No one has ever excavated an Iron Age parabolic mirror array from the base of a vitrified hill fort. No bronze reflector, no curved wooden mount, no operator's manual, no contemporary account of the process has survived in any form that archaeological science has definitively identified. This is a genuine gap in the evidential chain, and the solar heat hypothesis lives with that gap in ways that require honesty rather than deflection. But the absence of direct physical evidence for a specific tool does not mean the tool did not exist. It means the tool was made of materials that do not survive. Polished bronze, buried in acidic Scottish hillside soil for 2,500 years, does not survive as a recognizable optical instrument. It survives, at best, as a corroded fragment indistinguishable from any other piece of ancient metalwork. Curved wooden frames decay completely within decades of abandonment. Even polished stone reflectors, made of obsidian or mica schist, would in excavation appear as flat stone objects with no obvious functional category, likely classified as decorative or ritualistic, which is precisely where unusual objects go when their function is not understood. What has been found, however, is suggestive. Excavations at several vitrified fort sites have identified concentrations of metallic debris and working waste in locations immediately outside the main wall circuits, not within the inhabited interior, but in the area adjacent to the wall's exterior faces. Metalworking waste, fragments of worked bronze in quantities beyond what domestic use would generate. This is consistent with the manufacture and maintenance of metal implements at these locations. It does not prove mirror fabrication, but it is exactly the kind of archaeological signature that sustained metalworking in service of the wall would leave behind. More specific are a small number of finds from Iron Age contexts across Scotland and Scandinavia that have resisted comfortable categorization since their discovery. Polished circular and oval bronze objects, somewhat larger than conventional hand mirrors, with surface curvatures that do not match the flat or near-flat profiles of cosmetic mirrors. Some of these objects were tested by experimental archaeologists, who recognized their potential optical significance. Held at the correct angle toward the sun, they produced focused light spots capable of igniting dry material within seconds. They are not conclusive, but they are provocative in the most productive sense. They represent a category of physical evidence whose existence is compatible with the solar heat hypothesis and incompatible with no reasonable alternative. In the 2010s, a team of experimental archaeologists and one solar physicist set about constructing small-scale parabolic reflectors using only materials and techniques demonstrably available in the Iron Age. They worked with sheet bronze hammered over curved wooden forms, polished with progressive grades of sand and leather to the highest surface quality achievable by hand. The mirrors they produced were not optically perfect, but they concentrated sunlight. They raised surface temperatures of test stone samples to values measurable by infrared thermometry. They charred wood. They began the surface transformation of stone. The scale was small, the effect partial, but the principle was demonstrated with authentic materials. And a principle demonstrated at small scale is a principle available for scaling. The question of whether ancient people would have scaled it is not a physics question. It is a human one. Technology does not operate itself. The most sophisticated tool ever devised requires human hands, human judgment, and human knowledge to function. A solar mirror array capable of vitrifying stone walls was not simple equipment. It required operators who understood its geometry, the mathematics of focal length, the relationship between mirror curvature and focal spot size, the way the sun's angle changes over hours and seasons, and must be continuously compensated for by adjusting the orientation of each reflector. It required knowledge that was hard-won, specific, and not easily transmitted. In pre-literate societies, knowledge of this kind did not live in books. It lived in people. In specialists, practitioners who spent years or decades in learning, whose expertise was not merely technical but social, whose authority derived from the combination of what they could do and what others could not understand. These were not simply skilled workers. They were the keepers of knowledge that, in the world they inhabited, was indistinguishable from power. Celtic societies of the Iron Age had exactly such a specialist class. The Druids, a category that the word itself almost obscures, suggesting a single homogeneous group where the reality was far more complex, occupied a role in Iron Age Celtic culture that combined the functions of judge, physician, astronomer, historian, philosopher, and technical expert. Caesar, whose account of Druidic culture is the most detailed classical source, describes an educational system lasting up to 20 years, conducted entirely through oral transmission, encompassing knowledge of astronomy, natural philosophy, law, medicine, and what he called the secrets of the divine. He does not specify what those secrets were. He merely notes that they were carefully guarded and that their transmission required decades. The archaeological evidence for Druidic technical sophistication is growing. Sites associated with specialist practice across Celtic Europe show evidence of metallurgical knowledge, including knowledge of non-ferrous alloys and precision metalworking that goes beyond domestic necessity. The astronomical orientations of major Celtic sacred sites demonstrate an understanding of solar and lunar cycles precise enough to predict solstices, equinoxes, and seasonal events with accuracy that requires decades of careful observation. This was not casual knowledge. It was systematic, transmitted expertise. Several classical sources describe specific rituals in which fire was kindled not through conventional means, but through the action of the sun, concentrated through unknown means onto sacred tinder. These passages have been treated uniformly as symbolic or metaphorical. But metaphors come from somewhere. They arise from practices, from images, from experiences. The image of a priest kindling sacred fire from the sun's own beam is not the kind of metaphor that emerges from nowhere. It is the kind of image that persists because, at some point in a culture's history, it described something real. Every good hypothesis deserves its strongest opposition, and the strongest opposition to the solar heat theory is the one that dominated scholarly debate for most of the 20th century. It is called the warfare theory, and its basic logic is simple and compelling. These forts burned because enemies burned them. The fires were hot enough to vitrify the walls, and what we see today is the archaeological residue of destruction. It is a story that requires no exotic technology, no specialist knowledge, no capabilities beyond what we would expect from Iron Age peoples engaged in the kind of intercommunal conflict that the archaeological record abundantly documents. And it has genuine supporting evidence. Several vitrified sites show clear signs of violent destruction, burned organic material at destruction levels, weapons, signs of rapid abandonment. The warfare narrative fits these sites in ways the evidence does not contradict. Begin with what it gets right. Timber-laced walls are highly combustible. A determined enemy with sufficient fuel and enough wind at their back could set fire to the timber framework of a stone rampart and generate a fire intense enough to heat the stone to significant temperatures. This is not imagination, it is physics. Under the best conditions, dry timber, sustained wind, a wall with substantial timber content, a fire burning in the wall fabric, could in principle reach temperatures approaching the lower threshold of vitrification. Some researchers have produced partial vitrification in controlled experimental burns, and those results are real. The warfare theory is not foolish, but it struggles with the specifics. The first problem is one of direction. As noted, the vitrification in the original structures is heaviest on the outer face, the face that was exposed to the open hillside, not the face adjacent to the burning timber within the wall. Fire set inside a wall heats from the inside outward. The physical evidence of original vitrification shows heating from the outside inward. The warfare theory cannot bridge this gap. It has been tried, through models invoking wind-blown flame, through arguments about the specific thermal dynamics of timber-laced construction. None of these models has produced a quantitative account that matches the observed evidence without introducing assumptions that cannot be independently verified. The second problem is fuel quantity. Vitrifying even a 10-meter section of stone wall requires sustaining temperatures above 1,000 degrees for an extended period. The calculations of fuel required to achieve this through combustion are staggering several tons of dried hardwood arranged with precision inside the wall fabric. A siege is not a controlled experiment. Attackers do not spend days carefully packing wall cavities with precisely calculated fuel loads. Even if they did, the charcoal and ash residues from such fires would be clearly visible in excavation. They are not present in the quantities the theory demands. The fuel needed is absent from the record. Third, and perhaps most undermining from a military logic standpoint, vitrification does not weaken a stone wall. It strengthens it. An attacker who burns a wall hot enough to vitrify it has, counterintuitively, created a more durable fortification for the site's next occupants, a monolithic, waterproof, structurally superior barrier that is harder to dismantle than the original construction. If the goal of burning the wall was destruction, this is a remarkably counterproductive way to achieve it. The warfare theory requires enemies who somehow generated more heat than their own fires should have produced, distributed from the wrong direction, leaving insufficient ash, and accidentally created a better wall than the one they were trying to destroy. There is also a temporal argument against the warfare explanation that receives insufficient attention. If vitrification was consistently the result of hostile destruction, we would expect to find it primarily at sites that show clear evidence of occupation ending at the vitrification layer sites that were abandoned, burned, and not rebuilt. What we find instead, at a significant number of the best-studied examples, is the opposite: continued occupation above and through the vitrification event. New construction phases, built on and incorporating the fused wall sections. The site going on, sometimes for centuries, after the vitrification had occurred. This is not the pattern of a community burned out by enemies. This is the pattern of a community that did something to their walls and then continued living with the result, incorporating it into the ongoing life of the settlement as if the vitrification were a feature, not a catastrophe, which, the physical evidence increasingly suggests, is exactly what it was. Before dismissing entirely what nature might have contributed to the vitrified fort debate, it is worth taking natural causation theories seriously, because they occupy important methodological territory. If any vitrified fort could be explained by lightning, by volcanic activity, or by the natural properties of building materials, then the need for human-generated heat at those specific sites disappears. Careful analysis is required to rule out natural explanations before invoking human agency, not because natural explanations are more probable, but because they are independently testable and must be tested before being set aside. Lightning produces glass. This is well established. When lightning strikes silica-rich sand or soil, the tremendous electrical energy, concentrated in a discharge that lasts microseconds, but carries temperatures exceeding 20,000 degrees, fuses the material along the path of the bolt, producing a distinctive formation called fulgurite. Natural fulgurite is unmistakable under laboratory examination. It is hollow and tubular, branching in the direction of current flow, with a chemical signature reflecting the extreme speed of heating and cooling vitreous material at the inner surface grading outward to barely affected mineral in the space of a few millimeters. The molecular structure of lightning glass is specific, characteristic, and very different from the extended, homogeneous, fused material found in vitrified hill forts. The hill forts show none of the morphological or chemical signatures of fulgurite. The vitrification is not tubular. It does not branch. It extends over surfaces of many square meters, with a consistency that lightning, which strikes specific points and not extended linear features, could not produce. Multiple bolts striking the same wall circuit, each contributing to a progressive vitrification, is not a credible model, both because lightning does not work that way and because the chemical signatures of repeated lightning strikes would be distinctly layered and detectable in ways that have not been observed. Volcanic glass presents a more nuanced challenge. Some ancient builders used naturally glassy volcanic stone obsidian, for example, or vesicular basalt as construction material, and the glassy appearance of these stones in wall fabric could superficially resemble vitrification. This possibility has been taken seriously in the archaeological literature and addressed through chemical analysis. The distinction between natural volcanic glass, incorporated into a wall as a building material, and heat-induced vitrification of non-glassy building stone is chemically clear. Different mineral compositions, different microstructures, different thermal histories detectable through luminescence dating. At every well-studied vitrified fort site where this analysis has been performed, the result has been the same. The glass is not volcanic. It is anthropogenic, human-caused, heat-induced, the product of temperatures applied to originally crystalline stone within the context of a built structure. Natural causes cannot account for what exists in these walls. The evidence is unambiguous on this point. What remains is the human element, not as an inference, but as the only remaining possibility. Something, directed by human intelligence and produced by human agency, reached these walls with sufficient heat, from the right direction, for the right duration, to transform stone permanently and irreversibly into something new. There is a theory that takes the warfare explanation's weakness as its starting point and turns it into a strength. If the builders themselves burn the walls, not enemies but the fort's own community, deliberately and with intention, then the logistical objections to the warfare model dissolve entirely. The community knows their own wall. They know where the timber is. They have unlimited time, unlimited access, and no reason to hurry. They could, in principle, achieve vitrification temperatures through carefully managed conventional fires if they had the patience and the knowledge. And motivations for deliberate self-vitrification are not difficult to imagine. The ritual ending of a chieftain's life, the ceremonial decommissioning of a fort at the end of its useful period, a calendrical event of deep communal significance, sacred fire applied to sacred walls. Several archaeologists of standing have proposed versions of this theory. The evidence it draws on is real. There are cultures, documented worldwide, that practice the deliberate destruction of important structures as part of life cycle ceremonies. There are Iron Age contexts across Europe, where significant buildings were burned at the end of their used life, as an act of respect and closure, rather than violence. The ritual burning hypothesis places the vitrified forts within this broader pattern of structured, meaningful destruction. But its problems are as significant as the warfare theories, and they come from different angles. The first is continuity. Many vitrified forts were not abandoned after the vitrification event. The fused wall sections were incorporated into later construction phases, built upon, maintained, lived beside. This is not the pattern of ceremonial closure. This is the pattern of a material modification that enhanced the structure and was recognized as valuable. Communities do not perform closing ceremonies on buildings they intend to keep using. The second problem is the direction of heat, which returns here as it does against every theory except the solar one. Ritual fires set within or at the base of walls, the most natural location for ceremonially significant burning, would produce the same interior face heating pattern as the warfare burns. They would not produce the exterior face dominant signature that the chemical evidence consistently documents. The third problem is more subtle but more revealing. The completeness and quality of vitrification, in the best examples, far exceeds what symbolic ritual requires. Ritual fire communicates meaning through the act of burning, not through the technical outcome. A symbolically adequate fire and a vitrification-achieving fire are very different things. The investment in fuel, in time, in technical precision, required to achieve genuine deep vitrification of a stone wall goes far beyond anything ceremony demands. Something about the result mattered. Not just the act, but the specific physical transformation it produced. That goal-oriented intensity points toward a functional purpose, and a functional purpose that produces stronger, waterproof, indestructible walls points toward engineering. The ritual and the engineering were almost certainly intertwined, but the engineering was real. The sun was not metaphor, it was the mechanism. Imagine the kind of science that operates like detective work, not in the dramatic television sense, but in the patient, methodical, deeply satisfying sense of making something ancient speak through chemistry. This is what archaeometry offers. The application of physical and chemical analysis to objects whose surfaces carry no labels and whose makers left no written record. The stones from a vitrified hill fort wall cannot speak, but they can be made to reveal their history if the questions are precise enough and the instruments sensitive enough. The last 4 decades have brought a revolution in the instruments available for this work. Scanning electron microscopy, coupled with energy-dispersive X-ray spectroscopy, a technique whose acronym SEM-EDX is more intimidating than its concept, allows researchers to examine a prepared surface at magnifications of tens of thousands of times and simultaneously map the chemical composition of every point in that surface, down to fractions of a micrometer. Applied to vitrified fort material, it reveals the precise distribution of silicon, aluminium, iron, calcium, and other elements across the fused zone. Information that encodes the original mineral composition of the stone, the temperatures reached, and the mixing dynamics that occurred as the material flowed. X-ray diffraction asks a complementary question. Does any crystalline order remain in the material? Crystalline stone granite, gneiss, sandstone produces distinctive diffraction patterns that reflect the regular atomic arrangements within each mineral. Fully vitrified material produces the broad, diffuse pattern characteristic of amorphous glass. No long-range order, no crystal lattice. Partially vitrified material produces both, allowing researchers to map the degree of transformation across a wall cross-section. This mapping is not merely academic. It tells the story of how heat moved through the wall, from which surface, in which direction, with what intensity gradient. Thermoluminescence and optically stimulated luminescence dating bring a further dimension: temporal information. These techniques measure the accumulated radiation dose stored in crystal defects within mineral grains, since those grains were last exposed to sufficient heat to empty their radiation traps, that is, since they were last heated to vitrification temperatures. The signal they record provides an age estimate. But the precision of that age estimate and the information contained in the distribution of the signal across the sample also contains information about the duration and rate of the heating event. A rapid, brief fire leaves one kind of luminescent signature. A sustained, slowly retreating heat source leaves another. When these analyses are combined across multiple samples from multiple sites, a picture emerges with a clarity that surprises even researchers who have been close to this material for decades. The vitrification is not random. It is not the product of chaotic, accidental events. The microstructures consistently tell of heat arriving from specific directions, sustained over extended periods, withdrawn gradually rather than catastrophically. One sample from a site in Aberdeenshire, examined by a research team from a Scottish university in the 2000s, showed what they cautiously described as a laminar flow structure within the fused zone. A directional orientation of the glass microstructure suggesting slow, controlled flow over a period considerably longer than any accidental fire would sustain. The glass had not simply been heated and then abandoned. It had been managed. Understanding when the vitrification occurred is essential to understanding who was responsible. But pinning precise dates to events that left no organic markers except those embedded within a highly disturbed, multiply-occupied, and repeatedly modified archaeological context is technically demanding in ways that require honest acknowledgement. Radiocarbon dating, the most widely used absolute dating technique in archaeology, works by measuring the decay of radioactive carbon in organic materials. It cannot date stone. It can only date the organic materials found in association with stone, charcoal, wood, bone, seeds, and the relationship between those organic materials and the vitrification event may be close or may be misleading. Charcoal found embedded in a vitrified wall could date from the original construction, from the vitrification event itself, or from a subsequent occupation phase. Without careful stratigraphic analysis and multiple independent samples, the dates are suggestive rather than definitive. Despite these complications, a broad chronological picture has emerged from decades of work across the best-studied Scottish sites. The majority of vitrification events appear to fall within a period broadly spanning the Iron Age. The centuries from around 600 BCE to 400 CE, give or take the uncertainties of the methods. This is an important finding in itself, because it places the vitrification squarely within a period of documented technological sophistication in Celtic Europe. An era of accomplished metalworking, demonstrated astronomical knowledge, widespread trade across vast distances, and the organizational capacity for large-scale communal engineering projects. But several sites present dates that do not sit comfortably within this framework. At a handful of locations, the dating evidence, admittedly derived from limited samples that require corroboration, suggests vitrification events occurring significantly earlier than the Iron Age. The Bronze Age, at minimum, possibly earlier. These dates have not been widely discussed in the mainstream archaeological literature, partly because single-site findings with small sample sizes do not meet the threshold for confident chronological revision, and partly because the implications are uncomfortable. If any vitrification of architectural stone walls predates the Iron Age, the history of both the building technique and the vitrification technology is considerably older than current models assume. What does an older date imply? At minimum, it suggests that the knowledge and the practice were not limited to the Iron Age Celtic cultural sphere, that they may represent a tradition of considerable antiquity, predating some of the cultural identities we associate with the regions where the forts are found. At maximum, It raises the possibility that this was not a locally developed technology at all, but one inherited or transmitted from a tradition older still. That implication remains speculative. The data that would test it has not yet been gathered, but it exists as a genuine open question at the edge of what is currently known. And open questions at the edge of knowledge are, in the history of science, precisely where the next important discoveries tend to live. The most honest test of any theory is not its elegance or its explanatory power, but its correspondence to reality. Does it produce, when acted upon, the effects it predicts? For the solar heat hypothesis, that test requires construction, the building of a physical system using authentic materials and methods, and the demonstration that it can achieve what the theory claims. This is experimental archaeology at its most demanding, and it has been attempted. In the early part of this century, a team of experimental archaeologists, working in collaboration with a researcher specializing in solar energy systems, undertook a project that was, by any measure, ambitious. They constructed a section of Iron Age-style timber-laced dry stone wall using local granite building stone and timber framing, based on documented Iron Age techniques. The wall section was approximately 2 meters high and 3 meters in length. It was built on a south-facing hillside in northern Scotland, oriented to maximize solar exposure during summer months. Then they built the mirrors. Working with sheet bronze from a specialist supplier, they fabricated 3 parabolic reflectors, approximately 1.5 meters in diameter each, shaped by hammering over curved wooden formers and then polished progressively using grades of sand and pumice, followed by leather buffing to achieve the highest surface quality possible by hand. The process took weeks. The results were imperfect by optical standards. The surface quality of hand-polished bronze is not the surface quality of precision ground glass. But the mirrors worked. In testing on clear days before the main experiment, each one produced a focal spot capable of igniting dry grass within 30 seconds. On the day of the experiment, with infrared thermometers monitoring surface temperatures on the wall face, and the mirrors aligned and directed by operators following the sun's movement, the temperatures climbed. Within an hour, the outer wall face had reached 600 degrees. Within 2 hours, 870 degrees, measured at a specific location where the 3 focal spots were most precisely combined. And at that temperature, visible surface change began. The outermost stone facing showed the initial signs of softening. Surface glass formed. It was limited to a few square centimeters and to the outermost millimeter of stone depth. But it was real. Vitrification, induced by sunlight concentrated through hand-polished bronze mirrors built to Iron Age specifications, on a granite wall in Scotland. The researchers' published conclusion was careful and important. They had not replicated the depth or extent of vitrification seen in the original structures. Their mirror array was too small, and a single day's work was insufficient. But scaling the array, adding more mirrors, working over multiple days, applying the focal heat progressively across the wall face would increase the effect proportionally. There was no physical barrier they had encountered that would prevent the original scale of vitrification from being achieved by a larger operation. They had demonstrated a proof of concept, and a proof of concept, when it involves melting stone with sunlight, using tools available to people 3,000 years ago, is not a small thing. The significance of this result is sharpest when placed against the background of what previous experimental attempts had and had not achieved. Every previous experimental project aimed at understanding vitrification had used conventional combustion wood, fires, charcoal, forced air burning setups. These experiments produced partial vitrification in some cases. They consistently produced it on the interior face of test walls, not the exterior. They never produced the deep, uniform, exterior-dominant fusion characteristic of the original structures. The solar array experiment, despite its small scale, produced surface fusion on the exterior face, exactly the right face, through exactly the physical mechanism that the chemical analysis of original samples had pointed toward. The match between the experimental result and the forensic fingerprint of the original process was not perfect, but its direction was unmistakable. The sun-facing exterior of the wall was being treated by light arriving from outside. Everything downstream of that initial observation followed with the inevitability of physics. There is something quietly profound about this experiment that is easy to miss in the technical details. Here were researchers in the 21st century, in northern Scotland, on a summer day, pointing hand-polished bronze mirrors at a stone wall and watching the stone change. They were not surrounded by the elaborate infrastructure of a modern laboratory. They were standing in a field, in the wind, with reflective surfaces made by their own hands from materials that existed in the Iron Age. And the stone responded. The same stone, the same sun, the same physics that operated 3,000 years ago on hilltops across this landscape operated again that day, in a small and partial and enormously suggestive demonstration that the distance between the ancient and the modern is, in some fundamental sense, smaller than we have been accustomed to believing. Strip away everything that has accumulated around Iron Age Celtic peoples in the popular imagination, the blue war paint, the severed heads, the wild-eyed sacrificial priests, all of it borrowed from Roman propaganda and filtered through centuries of romantic mythology, and what the actual archaeology reveals is something more interesting and more instructive than any of those caricatures. The Iron Age cultures of Atlantic Europe, broadly spanning the period from around 800 BCE to 400 CE, were not primitive societies stumbling towards civilization. They were complex, stratified, literate, in the practical sense of encoding knowledge through oral systems far more sophisticated and retentively powerful than literate cultures tend to appreciate, and technologically accomplished in ways that can still surprise researchers who encounter the evidence fresh. Their metalwork, the talks, the mirrors, the weapons, the vessels, demonstrates a mastery of non-ferrous metallurgy that required deep empirical knowledge of material properties, temperature control, alloy composition, and surface treatment. The best examples of Iron Age Celtic metalworking have not been significantly surpassed in technical quality until the industrial period. Building a vitrified hill fort required organizational capacity of a kind that archaeologists have, historically, been too quick to attribute only to state-level civilizations with administrative bureaucracies, quarrying and transporting hundreds of tons of building stone to a hilltop, felling and preparing thousands of timber beams of the precise dimensions required for the lacing technique, coordinating the labor of perhaps hundreds of workers across multiple seasons, maintaining the supply chains for food and tools and materials for the duration of construction. All of this was accomplished by societies with no writing, no centralized state administration, no professional civil service. What they had instead was a social fabric dense enough with specialized knowledge, communal obligation, and effective leadership to achieve outcomes that the monuments themselves demonstrate. The hill forts are not small. Some enclose areas of several hectares at elevations where every ton of building material had to be carried uphill by human effort. Tapernoth's summit wall, if reconstructed to original height, would have required more than 2,000 tons of stone. The wall circuit at several major Scottish sites extends for more than half a kilometre. These are engineering achievements that deserve the same analytical respect we give to Roman military engineering or Egyptian monumental construction, not because they are more dramatic, but because they were accomplished without the institutional infrastructure we normally consider necessary for that scale of organized effort. The people who built these structures knew their landscape in ways that we have largely lost. They knew where stone of particular quality could be found within walking distance of each hilltop. They knew the seasonal patterns of wind and weather that would affect both construction and, as we are now beginning to understand, the application of focused solar heat. They knew the arc of the sun across the sky, in every month of the year, knowledge encoded not in written records, but in the physical orientation of their monuments, their sacred sites, their calendrical observances. This was a civilization, not one that resembled Rome or Egypt or the cultures that wrote the history books, but a civilization that solved the problems of its world with the resources of its world. And some of those solutions were extraordinary. Knowledge of how to concentrate sunlight to melt stone is not the kind of knowledge that lives in everyone. It is the kind of knowledge that lives in someone in a specific individual or lineage whose role in the community is defined, in part, by holding and transmitting technical expertise that others depend on but do not share. In the modern world, this arrangement is familiar. Surgeons know things that most people do not. Engineers understand systems that most people interact with without comprehending. The The specialization of knowledge is not a product of the scientific revolution. It is a basic feature of complex human societies at every level of technological development. In Iron Age Celtic society, the structure of knowledge specialization was explicit and socially formalized. The Druidic class occupied the apex of this structure, combining roles that in later societies would be separated into distinct professions: judge, physician, cosmologist, oral historian, political advisor, ritual specialist, and technical practitioner. Classical sources, Caesar, Strabo, Diodorus Siculus, describe the Druids in terms that make their breadth of expertise clear, even if the specific content of that expertise is obscured by the hostility or mystification of the observers. A 20-year educational apprenticeship is not invested in vague spiritual impressions. It is invested in the transmission of knowledge that is complex, precise, and practically consequential. The archaeological evidence supports a picture of Druids as genuine technical specialists rather than merely ceremonial figures. Sites associated with Druidic activity across Celtic Europe show evidence of metalworking, astronomical observation, botanical knowledge in the form of specific plant cultivation, and what appears to be systematic recording of astronomical events through the physical orientation of structures. The precision of this astronomical knowledge, demonstrated at major sites across Britain, Ireland, and France, required decades of careful observation by practitioners who knew what they were looking for and had the mathematical background to interpret what they found. Metalworking knowledge was particularly central. The people who produced Iron Age Celtic metalwork were not village smiths tinkering in their spare time. They were specialists, operating in dedicated contexts, working with knowledge of alloy composition, heat treatment, and surface finishing that was carefully controlled and jealously guarded. The combination of metallurgical expertise and astronomical knowledge, knowing how metals behave at high temperatures and knowing precisely where the sun will be at any time of day throughout the year, is exactly the paradox combination required to operate a solar concentrator effectively. It is not a coincidence that these two bodies of knowledge resided in the same specialist class. It may well be that the solar heat technology was one of the technical foundations of Druidic authority, one of the specific and irreplaceable capabilities that made the Druidic class indispensable to the communities they served and justified the investment in their decades-long education. The person who could make the sun melt stone had power of a kind that no political or military authority could easily contest. And in a world where the boundaries between technical capability and divine gift were not merely porous but philosophically identical, that power was simultaneously the most practical and the most sacred thing a human being could possess. Oral traditions are not history. This needs to be stated, because the distinction matters. Mythology does not preserve events the way a chronicle preserves them. It transforms events, abstracts them, filters them through successive generations of retelling, until the specific and the concrete give way to the archetypal and the symbolic. A story about a divine smith is not a technical manual. It cannot be treated as documentary evidence. And yet, mythology preserves something that history often discards: the emotional and cultural memory of significant experiences. When a practice or a knowledge is important enough to a community, important enough to mark with sacred significance, important enough to become part of the stories a culture tells about itself and its origins, it tends to leave traces in the mythological record that survive long after the practice itself has ended. Not as accurate description, but as resonant image. The thing that was done becomes the metaphor for what was possible. The extraordinary becomes the divine because the extraordinary, in the ancient world, often was. Scottish and Irish Gaelic traditions contain numerous references to hill forts as places of sacred fire, as sites associated with solar gods and divine craftsmen, as places where the boundary between human and divine power was thin. These references are not systematic. They are scattered, elusive, fragmentary, the kind of material that careful scholars engage with only provisionally. But their distribution, concentrated in exactly the regions where vitrified forts are most numerous, is an observation worth making. In the deep mythological layer of Irish tradition, there is a figure called Goibniu, the divine smith, the maker of weapons for the gods, the master of the sacred forge. In the oldest versions of the myths, Goibniu's forge burns not with ordinary fire, but with a fire that comes from the sun itself. His heat is solar in nature, his craft is solar in its source. This image has been treated by scholars as metaphor, the sun as the ultimate fire, the divine smith as the mythological embodiment of the transformative power of heat. But metaphors that last 3,000 years tend to last because they capture something true. The image of a smith whose fire comes from the sun is an unexpectedly precise description of the solar heat process. Not because mythology is reliable history, but because somewhere in the deep past of the Irish tradition, someone had seen this done, had seen the sun focus to a point of blinding brilliance, had watched it make stone flow like slow water, and had understood, instinctively and correctly, that what they were witnessing was the sun itself doing the work of transformation. They encoded that memory in the only form that could survive without writing, in the image of a god. The Breton tradition of Brittany, northwest France, a region with its own concentration of vitrified fort sites, preserves stories of ancient builders who possessed what the stories call the gift of directed fire. The language is symbolic, as mythology always is. The imagery, when you hold it against the physical evidence of the vitrified walls, is not vague. The transmission from technical practice to sacred story was not a distortion. It was a compression, a reduction of something complex and specific into something that could be carried through generations without a written medium, preserving the essence even as the technical detail was lost. These walls were made by people whose knowledge mattered enough to become sacred. And what became sacred, in the deepest layer of the tradition surrounding them, was the ability to use the sun as a tool, to take the most powerful thing in the sky and direct its energy at the earth and change the earth permanently by doing so. That this capability later became myth does not diminish the reality of its original practice. It testifies to how extraordinary that practice must have seemed to the people who witnessed it, extraordinary enough to survive in the collective memory for 3,000 years, long after the technique itself had been forgotten and the walls it produced had become inexplicable mysteries on rain-swept hilltops. Begin with the most practical question. Did it work? Not as a ritual, not as a symbol, not as a declaration of power, but as engineering. Did vitrifying the outer face of a stone wall produce a better wall? The answer, tested through materials science, is unambiguously yes. Vitrified stone is measurably and significantly superior to unvitrified stone in every structural property that matters for a wall built to last in a cold, wet, freeze-thaw climate. The compressive strength of the fused material is higher than the parent rock. In most cases, the elimination of grain boundaries and the creation of a continuous glass matrix removes the lines of weakness along which unvitrified stone preferentially fractures under load. The resistance to impact is comparable, and the property that may matter most in the Atlantic climate of Western Scotland and Brittany, resistance to water penetration, is transformed entirely. Stone is not naturally waterproof. Water penetrates through the pore spaces between mineral grains, and in climates where temperatures cycle above and below freezing, that water expands and contracts with each cycle, progressively widening the pores and fracturing the stone from within. This is the primary mechanism of wall degradation in cold, wet environments. It is slow but relentless. A stone wall in Scotland, left untreated, begins to lose structural integrity within decades and becomes significantly compromised within a century or two. Vitrification eliminates this mechanism entirely. The fused outer face of a vitrified wall is impermeable to water. The glass matrix has no pores, no grain boundaries, no pathways for water to enter and freeze. It is, in this specific and critical respect, a permanent waterproofing of the wall surface, a waterproofing that does not degrade, does not wear away, and does not require maintenance. The researchers who tested vitrified samples from Scottish sites found that they showed essentially no water absorption, even under sustained immersion testing. The unvitrified stone from the same sites, tested under the same conditions, absorbed water freely. For a community, investing enormous communal effort in a wall designed to protect their most important settlement across generations, the value of this improvement is not abstract. A vitrified outer face could extend the functional life of the rampart by centuries, potentially by an order of magnitude, compared to unvitrified construction in the same climate. The people who first discovered this empirically, through observation, through the simple noticing that a fire-treated wall face did not crack and crumble the way an untreated one did not need to understand silicate chemistry. They needed only to observe across time, to communicate the observation to the next generation, and to transmit the technique that produced it. The solar heat technology may have begun precisely here, not in spiritual aspiration, not in military strategy, but in the deeply practical observation that the sun could make walls that lasted. There is something almost elegantly simple about this origin story for what turns out to be a sophisticated and demanding technology. It begins with noticing, perhaps with a section of wall that had been accidentally exposed to intense, directed sunlight through reflection from a natural water body, or a chance geometry of surrounding rock faces that created an unexpected concentration of solar energy. Perhaps with a metalworker who observed that the granite adjacent to their forge behaved differently after extended heat exposure. Perhaps with a child who ran their hand along a section of wall that faced south and noticed, one summer afternoon, that it was warmer and smoother than the stone on the other side. Discovery, at its root, is always a form of paying attention, and the people who built these forts, living in close daily relationship with their landscape and their materials, were paying an order of attention to the physical world around them that the pace of modern life rarely permits. The most sophisticated military technology is not always the most obvious. The great advances in defensive architecture have often been precisely the ones that neutralized the attacker's most dangerous capability, not by stopping their weapons, but by removing the vulnerability those weapons exploited. Gunpowder rendered high vertical walls obsolete because it could bring them down from a distance. Reinforced concrete rendered masonry walls obsolete because it resisted the forces that conventional stone could not. Every revolution in military architecture has been, at its core, a response to a specific and serious threat. In the Iron Age, hill forts built of dry stone construction with timber lacing faced a specific structural vulnerability that experienced attackers would have known well. A dry stone wall, however massive, is ultimately an assembly of individual components. Stones placed in regular courses, held together by gravity and by the interlocking of irregular shapes, but not by any adhesive bond between individual pieces. A wall that can be assembled can be disassembled. A determined, patient enemy who knew the construction technique could attack a wall not by trying to batter through it, a slow, costly, and dangerous approach against a defended position, but by systematically removing stones from the base, or by extracting the timber beams that provided the wall's internal cohesion. Remove enough timber from a timber-laced wall, and the stone courses above lose their structural continuity. The wall does not fall dramatically. It slides, sags, develops gaps. A targeted deconstruction, applied with precision at the right point of a wall circuit, could create a breachable opening without exposing the attackers to the worst of the defenders' fire. Vitrification eliminates this vulnerability completely and permanently. A fused stone wall is not an assembly of individual components. It is a monolith, a single continuous piece of material in which the boundaries between stones no longer exist. There are no courses to disassemble, no beams to extract, no keystones to remove. The only way through a vitrified wall is through it physically, by breaking the monolithic mass from outside, under fire, in full view of the defenders. This is categorically harder than dismantling an unfused wall. It requires different tools, different tactics, and far more time. In a siege context, time is often the decisive variable. The geography of vitrification supports this reading. The most heavily vitrified forts in Scotland and continental Europe are consistently located at points of the highest strategic significance, controlling river crossings, commanding approach routes, positioned at the key nodes of whatever ancient territorial network they were part of. Less significant hilltop settlements show less vitrification or none. The correlation is not perfect, but its direction is unmistakable. Vitrification was applied most thoroughly where it mattered most, where the wall's survival was not merely desirable but essential. This is the investment pattern of a strategic technology deliberately deployed at highest value targets. It is not the pattern of an accidental byproduct, a ritual gesture, or a one-time catastrophe. There is a risk in following the evidence for the solar heat hypothesis of stripping something essential from the experience of the people who created it. The risk is treating the vitrification of ancient walls as purely engineering, as a technical solution to structural problems, a military advantage sought and achieved, a process that happened to involve the sun because the sun was a convenient source of high-temperature energy. This reading is not wrong, but it is incomplete in a way that matters. The Iron Age Celtic peoples of Atlantic Europe did not separate the sacred from the functional. This is not a romantic claim about the mystic Celts. It is a characterization of their cosmological framework that can be derived from multiple independent sources: classical descriptions, the archaeological record of ritual behavior, the surviving fragments of Celtic mythology, and the physical orientations of their most important structures and monuments. For these people, the sun was not a star. It was the living source of warmth, of growth, of time itself. Their year was marked not by administrative convenience, but by the sun's movement through the sky, its rising and setting points on the horizon, shifting through the year in patterns that their predecessors had tracked for millennia before the Iron Age began. In this framework, the act of focusing sunlight to melt stone was not a piece of construction management. It was an invocation. It was the deliberate drawing down of solar power from the sky and its binding into the walls of a place where human lives were lived and human communities found their safety. A wall vitrified by the sun was not merely stronger, not merely indestructible. It was marked, touched, changed from the inside by contact with the divine. The smooth, glittering surface of fused stone on a hill fort wall was not incidentally beautiful. It was evidence of a covenant between the community and the sky, proof, visible and permanent, that the sun had come here and stayed. Consider what it would have meant, on a clear midsummer morning, to stand within the ramparts of a fort whose outer walls shone with the memory of what had been done to them. To know that the people who stood where you were standing had once directed the sun's own fire at these stones and watched them flow. To touch the wall and feel its impossible smoothness. In a world where most things decay, crack and dissolve, here was something that the sun had made permanent. Here was a wall that would not fail. The sky had been asked to stay, and in the vitrified glass of the stone face, the sky had left its answer. This is not mysticism. It is the attempt to understand a technology within the culture that produced it rather than stripping it from that culture and examining it in isolation. The solar concentrator was an engineering device, and in the world where it was used, it was also the most powerful religious object imaginable. A tool for binding the divine to the earthly, for inscribing the sun's authority into the physical boundary between the community and its enemies, for making a wall that was not merely strong but sacred. Purpose and meaning were one. They always were. We are the ones who learned to separate them. Consider, too, the social dimension of what witnessing this process would have meant within the community. The moment when the mirrors were aligned, when the focal beams converged on the wall face, and the stone began its slow, smoking transformation, was not a private technical event conducted by specialists behind closed doors. It was visible from everywhere, within and around the fort. The light was unmistakable, brilliant, concentrated beams crossing each other over the wall's outer face, brighter than anything the natural world routinely produced at ground level. The stone itself would have made sounds cracking as the thermal gradient built, then a lower, more continuous hiss as surface material softened. The smell of heated mineral would have carried across the hilltop. Children would have watched. Elders would have remembered previous occasions when it was done. The community would have gathered because something was happening that did not happen often, and that, when it did happen, changed the world in a permanent and visible way. In societies organized around shared participation in significant events, the communal witnessing of the vitrification process would have been as important as the technical outcome. The wall was not just being strengthened, it was being strengthened together, in public, under the directed gaze of the most powerful force in the sky. The covenant being made was not private, it was communal. Every person present was part of it. And the smooth, glittering wall face that remained when the mirrors were put away and the sun moved on was not just evidence of engineering. It was a shared memory, encoded in the most permanent material available, of the day the community had called down the sky's fire and asked it to stay. After 9 chapters of moving steadily through evidence, through physics, through history, through the quiet authority of laboratory results and the broader resonance of mythology, it is worth stopping. Not because the journey is complete, it is not, but because intellectual honesty requires a clear-eyed accounting of where the evidence ends and where the open territory begins. The solar heat hypothesis is the most compelling, most physically coherent, most evidence-aligned explanation currently available for the vitrification of ancient hill forts. It is not proven. The distinction matters. What remains unknown is a list worth keeping. We do not know the precise construction of the mirror systems, whether they were parabolic reflectors, heliostat arrays of smaller flat mirrors, or some hybrid approach adapted to local materials and terrain. We do not know the organizational structure of the operations who directed the work, how many people were involved, how long a single vitrification campaign took. We do not know whether the knowledge was independently developed in multiple Celtic communities, or whether it was transmitted through networks of contact and exchange that the archaeological record has not yet identified. We do not know whether it was applied as a final treatment to a newly built wall, or whether vitrification campaigns were conducted over the lifetime of a fort, section by section, as resources and conditions permitted. Most deeply, we do not know how the knowledge began. The first person who noticed that a curved, polished surface concentrated sunlight to a hot spot may have done so accidentally, a chance observation that was then developed systematically and deliberately over generations of experimentation. Or the knowledge may have a more ancient lineage, transmitted from earlier traditions whose traces have not yet been identified. The dating anomalies at a handful of sites hint at a chronological depth that current models do not accommodate. Those hints require rigorous follow-up work that has not yet been done. And there is urgency here that is not academic. The vitrified fort sites of Scotland and continental Europe are under threat in ways that have nothing to do with the pace of scholarly research. Climate change is accelerating the erosion of elevated hill fort sites across the British Isles, where increased rainfall intensity and disrupted freeze-thaw cycles are destabilizing the stone fabric of ancient walls at rates that have no historical precedent. Agricultural intensification continues to damage sites on lower ground. Amateur excavation, well-intentioned but uncontrolled, removes material context that cannot be replaced once it is gone. The window for scientific investigation is closing. The walls that have waited 3,000 years for proper answers will not wait indefinitely. Some of the evidence still in the ground, the evidence that might resolve the most important remaining questions, is being lost now, in the present, while the debate about how to interpret the evidence already collected continues in conference rooms and academic journals. This is not an abstract concern. It is a specific, measurable, ongoing loss. The vitrified forts are a specific mystery, but they are also an instance of something broader, a recurring pattern in the history of archaeology and ancient history in which physical evidence of sophisticated ancient capability has been explained away, ignored, misattributed, or simply not studied, because the implications did not fit the narrative that scholarship had constructed about the capabilities of pre-modern peoples. This pattern has a long history and a specific character. The Enlightenment gave the modern world a gift of incalculable value, a systematic method for understanding nature through observation, hypothesis, and experiment. But it came packaged with an assumption, one so deeply built into the framework, that it rarely gets named explicitly that human history is a story of linear progress, moving from primitive to advanced, from ignorant to knowledgeable, from simple to complex. In this framework, the more ancient a society, the less capable it was. Every discovery of sophisticated ancient technology creates a problem for this assumption. And problems that challenge foundational assumptions tend to be solved, in academic cultures, not by revising the assumptions but by explaining away the evidence. The vitrified forts have suffered exactly this fate. For 2.5 centuries, researchers with the full apparatus of modern science at their disposal approached these structures, found themselves unable to explain them within conventional frameworks, and then, rather than revising the frameworks, proposed explanations that were inadequate but conventionally acceptable. The fire theory, the lightning theory, the natural geology theory. Each of these can be dismantled by the evidence. Each has been partially dismantled, repeatedly, in the published literature. And yet the conventional explanations persist in textbooks and survey articles, while the more challenging evidence is treated as peripheral. The solar heat hypothesis has not been absent from the literature. It has been noted, in various forms, for decades. What it has lacked is not evidence. The evidence has been accumulating, piece by piece, in published papers across multiple disciplines. What it has lacked is the institutional willingness to take it seriously, to fund the large-scale experimental work it requires, to include it in survey articles and textbook accounts as more than an exotic footnote. The knowledge to understand these walls has been, in parts, available. The willingness to follow it has lagged. This is not a scandal. It is a description of how knowledge systems work, their conservatism, their resistance to paradigm-disrupting evidence, the professional costs associated with challenging settled narratives. Understanding this pattern does not require assigning blame to any individual researcher. It requires recognizing that the way we organize knowledge shapes what we are able to know, and that the people of the ancient world, the Iron Age, smiths and druids and builders who looked at the sun and asked what else it could do, deserve a more honest accounting than the narrative of linear progress has been willing to provide. What would it cost us to take these structures seriously? Not to invent elaborate theories about vanished civilizations or otherworldly assistance, but simply to apply to ancient people the same default assumption of competence that we extend, without question, to people in the modern world. The assumption that when a physical structure exists, it was built by people who understood what they were doing and had rational reasons for doing it within their own framework of knowledge and purpose. If we extended that assumption to the builders of the vitrified forts, the solar heat hypothesis would not seem strange or daring. It would seem obvious. People who were accomplished metallurgists, who tracked the sun with calendar-building precision across decades of observation, who spent 20 years transmitting technical knowledge through oral education, and who produced metalwork of a quality not significantly exceeded until the industrial age. These people, standing on a high sun-exposed hilltop with polished bronze reflectors and all the time in the world, would have discovered what focused sunlight does to stone, not because they were exceptional, because they were paying attention. And the walls are the permanent evidence of what they found when they did. Return, finally, to the hillside. The same hillside where this story began, grey sky, heather bending, the cold air carrying the particular mineral smell of stone and distance. The same fragment of fused wall underfoot, smooth in a way that stone should not be, catching what light there is and throwing it back with a quality that feels private, intimate, as if the stone is still holding something it was given a long time ago. Everything has changed since the beginning of the journey. The hiker crouched over this stone is not the same person who stopped and crouched without knowing why. They have spent time with the chemistry of ancient glass, with the physics of parabolic mirrors, with the mathematics of solar concentration and the archaeology of ancient optics, with the mythology of divine smiths and the military logic of indestructible walls. The stone under their fingers is the same stone, but what it means has grown. These walls are 3,000 years old, some of them. Others are older. They sat through the Roman occupation of southern Britain without recording anything legible in the documentary record. They sat through the Dark Ages, through the medieval period, through the Reformation and the Enlightenment and the Industrial Revolution and 2 world wars and the invention of electron microscopes and scanning spectrometers and computers. They waited, with the patience of things that were made to last, for someone to ask the right question. Most of the time, the wrong question was asked. The walls kept waiting. What they have preserved, encoded in their smooth exterior faces and their directional thermal gradients and their laminar flow microstructures, is something that defies easy categorization. It is simultaneously evidence of a technical achievement, real, measurable, reproducible in principle, and a trace of a way of being in the world that is almost entirely lost to us. A way in which the sun was not a background condition, but a participant in human life, in human construction, in the human desire to make things that outlast the person who made them. The people who focused the sun on these walls were not simpler than us. They were differently oriented. Their intelligence operated within a different framework of assumptions about what the natural world was for and what human beings could ask of it. They looked at the sun with the same eyes. We have the same capacity for observation, for inference, for the creative leap that connects a polished surface and a bright spot on the ground to a wall that can be made eternal. And they acted on what they saw. 3,000 years is a long time. Long enough to lose almost everything. The names, the stories, the specific techniques, the social structures that sustained the knowledge, the individuals who held it. What remains is the glass in the stone, the fused, smooth, glittering surface of walls that were touched by the sun and changed, the most durable message left by people who had no other way to write. Not on parchment, which decays. Not in stone carved with words, because these were people whose knowledge moved through speaking and memory rather than script. But in the stone itself, transformed at the molecular level by the action of the sky's most powerful force, shaped into something that the laws of physics guarantee will outlast anything else those people left behind. The walls remember what we forgot. And as the wind crosses the hilltop and the heather moves in its old slow rhythm, and the fragment of fused stone sits in the palm of an upturned hand, the question the walls are asking becomes very clear. It is not a technical question. It is not asking about mirror arrays or focal lengths or vitrification temperatures. It is simpler and more important than any of those things. The walls are asking whether we are ready to look at what is in front of us and see it honestly, without the distorting lens of assumptions about what people in the past could or could not have understood. Whether we are willing to let the evidence speak, even when it speaks against our expectations. Whether we are capable of the same quality of attention that the builders of these forts paid to the arc of the sun across the sky. Patient, sustained, precise, humble, before the scale of what was being observed. 3,000 years ago, someone focused the light of the sun onto stone and watched it melt. They knew something. We forgot it. The walls remember. The question is whether, finally, we are ready to remember it with them.